what we discussed in the first half of the talk, Declarative C++, was all about how we can be correct by construction, how the abstractions help us, and what language facilities help us to be in the right spot and not have any issues, errors, or catch problems very early. We almost discussed how our code can be just a specification. And I actually wanted to discuss about one of the points which I hurried a little. I just go back on the last topic that we discussed to be sure. I wanted to make a couple of points. Okay. So we discussed was about the guarded shared object. So when you have shared objects, you want access to it very controlled. Okay, this is I'm talking here about a library which is created by uh, Ansel and Barbara. It's called as Copper Spice, and it is a superb library which actually helps us in managing access to shared objects. So here we had that's the GitHub link, and we are just talking about a plain guarded which will hold your object and it will also construct it. This one was fine. I wanted to make a point about uh, you know the the mechanism that was used, and it was about using a unique pointer and RAII to deal with things. So when you check out an object from this shared guarded object, you don't know whether it is you don't know how long it will be taken by the user, right? So there the scope managed unique pointer is really helping the cause here. And this with a custom deleter will make sure that the bookkeeping inside the guarded object is done properly. Okay. And so the only way to get it is via lock. I think this is pretty clear. And what you get is a unique pointer of the T. So you get the pointer to the T, which is inside the object with the deleter. Okay. And here, if you see it, yeah, the object cannot be used without locking, without by breaking the lock. Okay. So it is correct by construction and it cannot go wrong. Const correctness makes sure that you can only do const things with a const object and you can't do read write things on it. Okay, so the thing remains this, it's safe from concurrency issues, right? Data races, etc. Now here we have CTAD, which is a way of argument deduction, which was added in C++17. So you can have a very naive container like this in which you want to hold many T's. Okay, this is a simple object. This is the concept I wanted to just go back to. This is also a construction, a strong type, kind of a type-based enforcement. So if you create a C with 7, you know that you have passed an int. The container knows that it's an int, and the compiler will create a container of ints. So the type of T here will be deduced as int because of the 7 which is passed. But if you have a vector of doubles and you pass the iterator begin to end of the of that vector, you would be passing actually an iterator. And did you actually intend to create a container of iterators? Most likely not. That is what this would create. Okay, so it would not be what you're expecting. The T deduced here would be the iterator. And that is only if begin and end are the same iterators. We got a concept of sentinels, which could be a different type, which could represent the end of the end iterator. Okay. But if you have that, then both types do not agree what is passed here, and it might not create even a container of iterators, right? So here, the way CTAD solves the problem is we introduce a new constructor here, and the constructor has its own template. This T is different, which is the template of the type itself, and this T is a template of the container. So you can pass any type to it. obviously you have a template. But what to do with it? The only reason this container is existing is for it to say that when you get another type passed, in case there is an iterator trait for that type, then the value type of the iterator is what your containers type is. So as you see here, we use the trailing return type to say what data type will be returned in functions. But here we have the constructor saying that I will return this data type, which is a container of the value type of the iterator, right? It's so neat that just this one line, and you can actually make sure that I've just reproduced the same line above, that now when you have C7, obviously this was fine last time, but with a vector of doubles, now you are passing the iterators, and T is deduced to be doubles, and the container contents of V are copied over. All right. Now, when you pass 5 and 6, because 5 and 6 are just ints, and they don't have iterator traits, that's an error. Okay, I'm confused. Sorry about this. I think this is an initializer list, but isn't the container taking initializer list in its no, it is just taking one T. Okay, so it's just a toy example uh, from CPP reference. So it is just taking one T. It's a container of one element. So it's a bare minimum class that somebody was writing, and because of the name, I was thinking that there is a bigger storage, but there's just storage for one item. Okay, so that's why when two items are passed, 5 and 6, the compiler actually tried to check the CTAD, the type deduction based on whether it is an iterator, but the traits did not succeed because the numbers 5 and 6 are not really iterators. They do not have a contained type of value type. So it did not just work. All right. So this was the list of things. Composition really works. Strong types, value types. Use the model concepts. Let types model concepts. So enforce the concepts, variadic templates, fold expressions, and some types help. Small and separate composable small functionality can come together to make big ones. Generic implementations and specializations get you on track. Giving up options sometimes gives you more and exploit the strength, right? So if the code compiles, it works. Yeah, this was the point where we finished. So the section before focused on structure. Now let's look at behavior. So we have been saying that there are ways to influence the control structure. Okay. So let's see. So this was a function from the last session, which I'm reusing here. So as you see, this is a while loop. It starts with an I. It picks streams one by one, and based on some condition, it is doing flush and counting the stats accordingly. Now, you wanted to tell the processor exactly what to do. The processor felt something like this, like a backseat driver forcing it to do something. So really, how can we be less explicit in terms of control? So definitely the for loop makes the declaration as to how things are going. So we made that previous loop a for loop, and this now goes from the first element to the last element of the streams and picks it. But as we discussed, I think I pointed out in the previous discussion that the increment remained 2 times. There was a problem with the reference not taken. So this was a copy. Statistics could be an atomic operation, and system threshold was a dependency on global. Okay, this is a slight deviation from that previous slide, which had a number here. So this dependency on a global makes this function, influences the operation of this function. Which stream will be picked at which time depends on what value is there in system threshold. If that changes, your same function with the same kind of input will do a different behavior. Maybe it will pick some different um, strings to do its job. So first of all, let's make it more declarative. So we just get rid of the indexes, and rather than saying, okay, do a +1 on the indexes and access them by index, we just say we want to go through all the strings. Okay, that the less code you write, the less code will go wrong. And the compiler very well translates this very, very correctly. Okay, now system threshold, obviously, like we discussed, is a global variable which is used here, and that makes this function impure and indeterministic because we don't know what the value of global is at different run times, at different times that this function is invoked, right? So we would not like to do that because we like local reasoning. If you're seeing one function, if you can determine all its behavior by just looking at that function, you have a very good implementation and it is understandable by even somebody who's just picked your code today. But if it is depending on previous knowledge and what the system might hold, is it really a configured value or a calculated value? Does it change? Who knows about all of that? And your system becomes such a small function still becomes unexplainable, okay, or indeterministic. So I'm using the word pure and impure. So let's look into what it is. When you have an external dependency, uh, it becomes painful to understand. If you have completely local functioning, then it is very easy. It is right in front of you. Hard to test. Impure functions are hard to test, while pure functions can always serve themselves, render themselves very easily and very well to UT and be very well testable, all the possibilities, etc. Because you have full control. It only depends on the arguments passed to it and not on anything external. It's a very good property to have. Now it is difficult to debug when something else can influence your functioning rather than uh, very quick turnaround times with pure functions. So even in your object-oriented code or any procedural code, if you are writing pure functions and more pure functions, that is something that you should strive for. Okay, and it is not easy to parallelize because there is external dependency and there will be threading locking, I don't know. And this one is really easy to parallelize. If you just give this work to this thread or this function, this job, it will do the job and come back. It does not need anything else in the world. Perfect. Good quality to have in a software, right? So how do we remove that? So now this only depends on the past arguments. We have removed the global dependency going outwards. We have passed the parameters. So obviously, this is much better than the previous version. Okay. Now, if you had to, this is flushing the strings. Okay. This is the main operation and this is the stack incremented. Now, if you had to dump errored strings, what would that look like? Now, it is painfully similar, but yet not the same. This is also having a loop. It is having some condition. I've been marking the lines for the last couple of slides. This is doing a different operation and incrementing a different stack, but it is painfully, you can see it is just the same. So what to do? Factor out the decision and the action that you have been taking into a predicate. We got lambdas, they make passing functions, operations very easy. Okay, and it can carry its local state as well. So they are perfect for passing as predicates and actions for small things. If you have something big, then perhaps you can pass any executable here. And so we have a predicate which is helping you decide the condition and the action which is actually doing the work. So whatever is passed will be used. Now both flush and dump look the same. They are actually ended up being the same, and you didn't have to duplicate this code. It starts to look like how algorithms would be developed, but the standard library algorithms would be very much more different, and we'll touch upon some aspects here. Okay. but let's name it well. It is not flush streams anymore. So what do we call it? Let's say for each if. So you want to do something for each stream which follows, which obeys which meets a condition, I'm sorry, and take a particular action, whatever is passed. So this is what it looks like. STD invoke was a facility introduced in C++17, which helps you invoke uniformly any executable, any function or callable on an object. Now, function and callable are anyway invocable. If you have a lambda, you can pass an s to it if it is matching the type. If you have a function, you can pass it. If you have an std function, you can pass the object. If you have a function pointer, you can pass. So the way invoke works is that it takes care of a member function also, which cannot be called the same way as the other functions which we just discussed. So in order to call a member, you will have to call s dot star of that function pointer, member function pointer. Okay. I don't have it written in the slide, but I hope you get it. So the way to call a member function is s dot f, that will call the f member function. But if you have a ptr to f, okay, so the way to call would be to dereference the ptr to f and then call on s. That means this line is not the same if depending on what kind of function you have passed. Okay, so if you passed a free function, it can just be called by just naming the pred and passing the in parentheses the s to it. But if you call a member function, that line will have to be different. Now, how do you make generic code if both are possibilities and you want to support them? That's where the invoke comes in. Invoke takes care of the right way of invoking this predicate on by passing s to it, and that's the beauty of invoke. And so I've used invoke in both these places, and that will be the right thing to do. Now the user is, you have enabled one more case by doing something generic and taking care of the variation in the expectation in the code that runs it. By doing that, by using invoke, now your algorithm is more generic and handles more cases. You have allowed the user to pass even a member function pointer. Okay, and now the caller takes all the calls and has full control. Okay. Okay, so this is how you can extract decisions out into a callable. You can extract the actions out into a callable, and you can still continue to write generic implementations. Okay, now the flow, you have full control of the flow. And now this algorithm, once written very generically, so we have not written it, made it generic for the type T of the vector. It is a fixed type of string, but you can imagine that we can now add T as a template parameter, and now it is truly generic. Of course, you'll have to provide other overloads if you want to support execution, parallelism, etc. All right. Any questions? Stop me, okay? I don't see any on the Q&A, so I'm proceeding. Okay, explicit predicate and action. Okay, now what does flush streams really look like? Now you have a functionality called as for each if, and now you can pass to it the streams that you really want and the two functions based on what you want to see. Now you are really plugging in the functionality that you want, and similarly dump streams would just plug in different condition and a different action, and actually the logic is the same. So don't repeat yourself. You have actually made a generic functionality out of both the things. So I have highlighted the conditions different in both cases and the actions which are different in both cases. All right. The functions only take domain level decisions and do not do low level actions. So now these flush streams are at a higher level. Okay. Didn't we want to do that? It was our goal. So stay high level, make a functionality which can be used and reused. So you have reused, and once you have proven that that is correct, it will continue to be correct for next users also, and your code continues to be more and more correct, and you fall in that beautiful spot of correctness by default. Only if you do not write one more time that functionality which can make things go wrong. Okay, so now let's look at ranges. Now, what would the flush streams look like in ranges domain? So I've just extracted the two uh, lambdas which were being passed inline. I've just named them outside. So we call them over the threshold and flush. Flush is the action, over the threshold is the condition. So by naming these two, I can now write the ranges version of the same algorithm. Now I have the streams and I'm piping all the entries of that uh, into a filter which says use only entries which meet this condition. Okay, and for each, then you iterate through that. So what does this do? This just creates a pipeline. It just creates uh, a, a series of operations which would happen on the items of the streams when iterated. This is just a declarative definition of the operations that will happen on the items in streams. Okay. And so in this case, there's just one step, which is the filter for over threshold. But we want to do flush after that, and that's the terminal last operation. So we make this into a view. Okay, so you have the streams vector, and now you have said that I want to make a filter view over the streams so that when I iterate in this fashion, as streams over the threshold, we can actually go only through those items. Only those items will be emitted which meet the condition. If you just go through streams, you will touch everything and you'll flush everything. But now that you have made streams piped into this filter as a view on that container, you are now able to iterate through that view on the items of the container. Okay. And so we see both here range adapters and range factory uh, uh, adapters and factory and range algorithm style. Uh, we'll discuss a little further also. So ranges can take any callable, right? Member function pointers, std function, any callable is fine. And it should be able to accept the type which is coming from the previous stage. And you can pipe as many stages as you wish. Okay, finally, the looping through the things happens here. Okay, if finally, I think I did not include a slide here, but finally, if you want all the entries which make it to the end of the defined pipeline, if you want all of those saved in, let's say, a vector or in another data structure, then you can just at the end say pipe ranges 2. So 2 is another range adapter which will create a new container and hold the entries there. So very smart, and that is the entire representation of the loop, and very declarative, step by step. And all you have to review is not what views does, not what filters does, but you just have to look at your lambda or your function, which is the little one line which you have written. And again, you will be in a sweeter spot for correctness. All right. So I see Sumit Kumar has put a comment that there would be a review comment on the last line. You have to tell me what it was. And sorry about that in advance. Okay. So ranges adapters. So ranges can be adapted by views. You want to see at a particular aspect or in a different way or with some uh, filtering or some transformation. These are the kind of things that range adapters do. I've just shown some things here. So if you want to just see the keys of a map, you use the views keys uh, adapter, and you are going through the map here, but only with the keys. So only the first element of the pair would be seen. And if you print this, as you see here, 1 and 2 will be printed, which is the key of the map, and nothing else. So it is a way of looking at just one part of what the map gives. Okay. If we go to range adapters further, you will not only see that there is keys, but as you expect, there will be values also, right? And here we have a vector. This time it's not a map. We have a vector which has a tuple of a string to double and bool. Okay. Now this is it's an interesting field of quartz, and so the entries are tuples, up, down, charm, strange, and top, bottom, and various values of double and bool have been mentioned. Okay, so this consider this vector, and let's look at what we can do with this. Can we do keys on it? Answer is yes. The first item of a tuple is a key, because a pair is also a tuple, is nothing but a tuple with two items. A tuple is more generic, it can hold many. Okay, so uh, if you want to see just the first one, you call it keys. Okay, if you want to see the second one, you call it values. So we are just looking at the quark mass charge, the same vector, okay, but with the values part, which implies the second one. Okay, and now if you want to see the third one, we have something called as elements, to which you can give uh, a constant, and that constant decides what is the index of the element that you're choosing to go through. So again, all these three are very equivalent. This one is picking the first one, second one, and the third one here in the last one. And you can expect this to print something nice based on the contents of that vector. Okay, so let's look at range algorithms. So we know there are algorithms in the standard library already, but ranges also came up with algorithms because we were all bored of passing iterators. The case of passing iterators was when you maybe don't want to go from begin to end. But most of the time, with some definition of most, we really do want to go through the entire container. Okay, so here we have a container V, and we want to find the min max element. So there is a ranges version of it, min max element, which takes the entire vector. It recognizes ranges and it is able to iterate through the begin to end of that range. Okay, and you can create a sub range out of a whole range. So all that is possible. So you can do a shorter version if you want, but at least you're not taxed every time to pass begin and end of every vector or every data structure that you want to work on. Okay, and so now when you calculate the distance between min and max, I think you will get the right values. Okay. So it's good. You are able to express your intent directly. But something that the range algorithms don't have is the parallel version, which the algorithms version do have. So if you have like there is an array of two items and there is a vector, if you want to do a for each of parallel execution, uh, for A begin to end, you can do it this way. If you just say execute in parallel, it will create different jobs for the different entries, and it will be able to process them in parallel. Unfortunately, you have entered a database where you want to read the item. Where is I? Okay, whatever is passed. So every item is passed and in pushback. Now two jobs are running in parallel, and they are both trying to push back without any uh, synchronization primitives. Okay, so this would mean that the vector is now being bombarded parallelly, and it is a database. So you can run into issues when you do something like this. So you have to be careful, and you have to make sure that you are locking uh, or using other means to make sure that you are in good mutual exclusion. Okay, again, this is with part. So there are at least three is what I know, 3 or 4. So execution SEQ sequence is what tells the algorithm to go one by one. PAR parallel tells it to go in parallel. So everything can happen in parallel. there is unsequenced or parallel unsequenced, par unseq, par underscore unseq. So parallel unseq is going to tell it to use SIMD also if possible, and so it might run in any random order. It's not guaranteed, and I think only unsequence is also there. So if you have sharing, you might really reconsider doing it parallel. But maybe you have done it right, and you can use the parallel part of it. So please do. Uh, if your data does not have mutual dependency, like first entry, second entry, third entry, when being worked upon, it will not have you know contention between them. It wouldn't be a problem. Okay, so right now, uh, X is incremented. Where is X? It should be this. This should be X, I guess. Oh no, X is a global. Oops. So X is a global and that is being incremented. This is an example from uh, CPP reference. I liked it, so I kept it. Okay, so we also have coroutines which tell you how you can save the context in resumable functions, right? I hope you know a little about coroutines. They so you can invoke them, uh, come out early from them with some value, intermittent value, and keep the context right there, right? So, and then next time you enter the same function, you will resume from where you left. Okay. So this section is about coroutines and generators. So I just checked the one of the questions which has just come. If you use mutex within parallel execution, then parallel will not be faster and it will actually behave like sequential program. No, it is probabilistic. It doesn't mean that everybody reached the mutex lock at the same time. And let's say there are 1 million entries and 1 million threads are created, and all the 1 million are right now sitting waiting for the mutex so that only one by one they will go. Maybe some threads or execution context or tasks started late. So it might be fine. You might not see. This is a problem with concurrency things. So you have to be careful. And this assumption is not right that it is sequential. It is in some random order which cannot be predicted. And every time it might be predicted. It could be different. Okay, thank you for the question. Okay, so coroutines. Now let's consider a simple tree like this. There is a left node and a right node, okay? And every node has a value. Okay, very simple, bare minimum basic tree. Now, if we add a function which is supposed to traverse in order on the tree, so which means you go to the leftmost first and then go center and then go right, okay? And up and down the tree. But what we want is this order, this traversal is going to, as we discussed, so it is in order, it goes to left first. If left is there, then you traverse it, okay? And if you found a leaf node, or if you found a the last node which does not have a left, no, sorry, if you found the node which is the leftmost, yes, then you yield that value, and then you traverse the node which you found uh, uh, the node which is the parent of left, and then you go to the right side so that it is in order, right? Because we expect in a tree, left is smaller than the right. Okay, so this one is checking left. It is traversing the left in order and it goes recursively perhaps, and then finally it gives the leaf node reaches a point where there is no further left child. So it is the leftmost node and this value is being returned. So this co-yield is is a return without losing the frame of that, without losing the data of the context here. Okay, so any variables, local variables here are saved in something called as a coroutine frame. and we have stackless coroutines, so they are dynamically allocated. I might be wrong. I'm not 100% clear whether it is dynamically. I think it is. Yeah, I think it is dynamically allocated. So it is kept for later. And you can see, imagine how much the compiler is is keeping, is managing for you. You didn't have to say anything. You just said, I want to yield early from this and want to come back and resume at that point next time I get this call. That's what coroutine does for you. The compiler is managing the entire state, all the local variables in that coroutine frame, and then resuming next time you call this function, right? So it's just great. You can imagine how much the compiler is working for you and how much we can exploit it. And this gives you, despite it being a context where things are stopped and started and stopped and started, and then there is of course, some other things are happening. So there is a concurrency concept, context here, but you don't have to manage anything by just writing co-yield or co-return, right? So it's just, it's very beautiful how much work the compiler is doing for us. So, and that's why, despite picking and dropping all the context, we can still traverse this pretty much linearly. This is how you would write single-threaded code, or non-concurrent code. And here you are writing concurrent, but without much value. Instead of saying return early, return, you are just saying co-yield. Okay, so co-yield will give back the value of X here. Give out the value of X. All right. So this is what this function would do. It would create a generator. Generator is a specialized class which would keep on maintaining the context and calling the generator. Adds functionality over the coroutines, and it makes it like a callable which can resume. Okay, and we can see that in the next slide I've shown. So this is a way, this is how the tree is there, and the diagram represents pretty much how the tree is organized. So this is a tree, and that's the same data structure that we saw, which has a left and right. And this tree has a tree +1 as the left and +2 as the right. Okay, so D is the root node. It has a B as the left and F as right. B is a node itself, and it has A as the child and C as the right child. A as left and C as right. F has E as left and G as right. So if you see in terms of a tree, this is very correctly ordered in terms of of an in order traversal. You see A is the leftmost leaf. Then the next you will traverse. If you have to manually traverse this, you will traverse B, which is the next node. Then you traverse to the right of B. Then you go to the parent of B, which is D. And then because you are done with the left side and you have traversed this node, now you go to the right side. So after D comes the F node, but F has a left child, so you'll go deep, deep, deep all the way into the recursion. So anyway, so you see it comes to E, then F, then G, and you see this is printed in order because the tree is really placed in order. All right, so that's what the for loop here does. This generator is what keeps the traversal going. And again, for what cost of your own? How much did you have to write? Barely anything. So it's great. So we have higher level functions coming from programming style. We have pure behavior. We want to have no side effects. So it should neither depend on something outside, nor it should cause a different change outside as per functional programming. Okay. Of course, programs exist to cause a change. For example, you want to save a new record to the database. A new employee has come. That's why you are adding the entry. Maybe you delete some rows from delete your photos. So you want the file system to change. And so you want external change, but let it be contained is what the suggestion, the recommendation is. So you can have these parts in your program. After all, that's why you wrote the program. Functional really encourages against and contains them in dedicated functional aspects. You can pick and choose. It's C++. You have the choice, but uh, make your programs composable and create higher level functions which depend on lower level functions. And that's the composition on the behavioral side. We saw how loops are transformed into a pipeline, and that's the representation of a loop. And the decisions are taken out in a predicate. They are there somewhere, but the dirty parts are encapsulated inside a set scope. And in fact, there's some slides which are missing here. I wanted to show to you STD optional and expected, uh, which actually have continuations which you can state at the end of it. So sometimes, let's say you're looking for an employee, you may find the employee, or you may not. So the return type of that is an optional, and optional now has a way to say, uh, what to do after that. So optional has monadic interfaces called as a function called as and then you pass a lambda to it. So whatever value the optional has, if it got a value, and then will make sure that the next step you have given to it by just saying that I want this done, this is the next step, and it will execute the next step once optional gets the value. Okay. Similarly, for expected also, you can say what should happen when there is an error, or you can say what should happen when there is a value. If you didn't get a value, you can even say if you didn't get a value. If you got a value, you have an operation to do. But what about the else part? Even for the else part, there is a monadic extension called as value or. So you can say if the value did not come from the function, use this value. Okay. So scope based is an important thing when talking about flow. So we have, let's say, we want to make sure that some of the operations definitely happen at the end of leaving this scope. So here we have a function which is counting the metrics and stats, and you're being smart. You're not calling the atomic increments of global stats, and depending on global, you are managing it locally. But finally, when you leave, you want to submit the stats to global stats. Okay, this code is perfect, right? No problems. Why should I talk about it? Is it possible that stats are not uploaded even when you wrote the code? So the devil is in the detail, in the dots, and there are 6 of them, if that makes any sense. So there could be exceptions, and which would be a different way of leaving the scope rather than leaving from the last line. So you might never hit that line. So you counted all the stats, but you never submitted. This you don't want, okay? And you can have many similar needs in your programs. So what do you want? You want this to always happen. So what always happens when you leave a scope? Since it is online, I'll not wait a lot. Always something happens is local variables are destroyed. So why don't we create a local variable? Okay, so this is that second line is creating an object called a scope exit, which takes a callable. Yeah, local stack clear. Thank you very much for the answer, Ashutosh. So you pass a lambda to it by saying that on exit, you have to do this. I named the variable on exit. The real functionality is called as scope exit. Please note, I have not written std here. I'll come to that. So whenever the scope, this variable is created with a lambda, and you know what code to write inside it. In its destructor, you have to invoke this f. Okay, whatever lambda is passed to it. Till then, you'll have to hold on to it, right? So you have a reference to that stat. It is all local, so all fine. And when this goes out of scope, first on exit will go away, and then the stats will also go away. So all is well here. And once you have declared that I want this to happen at the end of the scope, this will happen. In Java, you have something called as finally as a separate loop construct. In Go language, you have something called as defer. and defer you give something like this, like that, later this should happen. Okay, so RAI just works. I guess um, they came up with their own names, and we still don't have this functionality because this is inspired by experimental scope exit. I don't know if this is making it into this, being passed as a string. Okay. Okay. So something that I didn't cover in my slides in terms of functional operation is uh, I wanted to uh, at least something which is already available to you is when you want to create threads and you want to create jobs for for many items which you have in, let's say, a vector, you can just iterate over the vector and call async on it. It will create the job, and not only create the job, this much the compiler is doing for you, that it is creating a thread, it is running the function which you give to it to run in that thread, and also collecting the return of that function and giving it back to you in your current thread. All of this work with you spending, not breaking a sweat, just wishing for it and asking for it. So use async where you would otherwise create a temporary running thread. But of course, you have your own overheads of creating a thread and a thread executing in your system. So if you are conscious of that, then there are packaged tasks which you can create. Okay, and STD execution is coming in C++26, which will allow you to have jobs, uh, tasks created and run in executors, just like you ask for something to be done in a thread pool, just that way. And you will again be able to chain continuations on it. So first do, let's say, first open a file. Next, look for these lines, n number of lines. Then. So you can follow it up with many tasks. And there, in a very, I'm really sorry, I don't have a slide for it. I should have brought that here. In a very declarative state, you say first this should happen, then that should happen, then that should happen. And this will happen in a asynchronous way when the result is ready and the continuations are able to run. And this is all checked at compile time in terms of what we discussed in the first session, that the types have to match. The return types of the first stage should be the accepted arguments of the second stage, and so on till the entire chain that you create. You can even say what should happen in the exception case in case an exception happens. So there is a lot of leeway. You can have multiple schedulers in your system, and you can move jobs from one scheduler to the other one. All of this by just asking for it. By this is what the standard library is providing. Somebody's written that code, and we should be able to use it and reuse it because they have a solid implementation. Okay, so there's all of this good stuff to look forward to, and all uh, these facilities that we discussed in the 2 hours that we happen to discuss in. Uh, a lot of these facilities are available right away since years, more than a decade, some of them, and many of these facilities are being worked upon. A lot is coming in the upcoming versions of C++. So I'm sure you'd be interested in knowing all of this. Keep track. If you learn about anything new, please feel free to come and give a talk at CppIndia. But for now, I will just say that simplicity is the ultimate sophistication. If you are able to say something simply, if you are able to tell something to a 6-year-old, explain something to a 7-year-old, you have got it. And we are getting very close in some respects in C++. So make sure you make the most of what you already have and keep upgrading your compiler versions and language versions. So that's it from me.